In Chapter 8, we're going to kind of do a high-level pass on IP addressing. This is not subnetting, but it is somewhat of an introduction to the subnetting concepts and manipulating IP addresses and so on. I think you guys will find that this particular section is extremely valuable because it will further solidify your understanding of how these devices communicate, how they make decisions, and so on. All right? So let's get started. With regard to IPv4, we know that we use a specific address format called the dotted decimal format. IPv4 addresses are 32 bits in length, and as such, they can be written in blocks of 8, what we call octets. This is the first octet, second octet, third octet, fourth octet. We call those octets because each one of those decimal representations represent 8 bits because an address is 32 bits in length. A subnet mask is also 32 bits in length. We'll talk more about subnet masks later on. So if you were to write this out kind of in a way to understand it, it would be 8 bits dot 8 bits dot 8 bits dot 8 bits. Now the reason why I'm specifically saying that is because that makes a difference when we start to look at how addresses are represented. Even when we go into IPv6, IPv6 addresses are written in a particular format. We'll have to understand that. Each one of these octets can either be represented as a string of 8 ones or zeros or as a dotted decimal number. Now we talked about yesterday in one of the previous chapters, we talked about the concept of the radix scale, right? 2 to the power of 0, that's my least significant bit. 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. Now remember guys, on the exam you don't get a calculator, and you are going to have to do powers of 2 calculations. Well, one of the things that you will have an opportunity to do when you sit down to take your exam is they're going to give you a dry erase board and they're going to give you a marker, and you can write down your powers of 2 scale. You can't bring it in, you can't bring anything into the testing center, but you can certainly write things down before you go to the first question. I would highly recommend, no matter how good you are with this binary math, highly recommend that you write down your powers of 2 scale at least up to the power of 13. Because that's, we don't worry about that with an address, but there are some calculations that you'll have to do up to that power level, up to that 2 to the power of 13 level. Okay? So make sure that that's one of the things that you jot down. Let me mute this person. No. Why isn't it muting that person? Mute. Somebody just joined and they did not mute their microphone. It sounds like they're making dinner. Yeah. Okay. All right. So we're going to review this again because it's important. 2 to the power of 0. 2 to the power of 0 is equal to 1. 2 to the power of 2, of course, is equal to 2. Excuse me, 2 to the power of 1 is equal to 2. 2 to the power of 2 is equal to 4. 2 to the power of 3 is equal to 8, and so on. We call this bit the least significant bit because it has the lowest decimal weight. The decimal weight is represented in the octet bit values row, that third row. This is the decimal weight. The most significant bit is 2 to the power of 7, which has a decimal weight of 128. And very simply, if I want to represent a binary number as a decimal number, I add up the columns that have a 1 associated to them. I circled ones that didn't, but you get the idea. You add up the columns that have a 1 associated to them. So in this case, the 128 and the 64 column, they are turned on. Add 128 and 64, you get 192. Conversely, if you want to convert the other way, if you have a decimal value and you want to represent the binary equivalent, you turn on the columns that add up to that decimal value. So for 10, it would be 0, 0, 0, 0, 1, 0, 1, 0. Very simple. Okay, because the 8 and the 2 added together equal 10. You guys agree with that? Agreed? Yeah. All right. As I said yesterday too, the number of bits that you need to represent a decimal number depends on how large that decimal number is. In our particular case, there's only 8 bits in each octet, which means what is the lowest possible decimal value I can have?
So one of the questions would be to translate from IP address to binary numbers.
Right. They're not going to do something like that on the test. They're not going to have you convert from decimal to binary and binary decimal. However, there are calculations that you're going to have to make that require you to understand this process. You follow what I'm saying?
Yes.
Now let me repeat my question. Because this is an octet, what is the lowest decimal value I can have? The lowest decimal value I can have represented in an octet is 0. The highest decimal value I can have in an octet is? Right. There are 256 possible values that we can have in an octet. 0 is inclusive. All right? Now remember what I also said about the scale. If 32 is this column, all ones to the right of that is equal to 31. If 16 is this column, all ones to the right of that is equal to 15. If 128 is this column, all ones to the right of that is 127. 128 plus 127 is 255. Make sense? All right. So here's our radix scale again. 2 to the power 7, 6, 5, 4, 3, 2, 1, and 0. This is the place value, 128, 64, 32, 16, 8, 4, 2, and 1. So if I turn on the 32 place value, I turn on the 2 place value, I turn on the 1 place value, that is going to equal to 35. The decimal equivalent of 35. And vice versa. We're just looking at a couple of different examples here before we move on to the next part of this discussion. 192.168.4.6. Hopefully, if you look at this now, you understand how I got 192. I got 192 because the 128 placeholder and the 64 placeholder are turned on. 168 is 128 plus 40. So 32 and 8 is 40, plus 128 is 168. You follow what I'm saying? 128 plus 32 plus 8 equals 168. Because that's 40 plus 128. All right? All right. However, IP addresses, they're very easy to work with. They're very easy to deal with. But an IP address is not the only thing that we concern ourselves with when it comes to network communication. In fact, it's not really the most important aspect, at least not fundamentally the way the host communicates. It is extremely important that you understand what the effect of a subnet mask is. IP addresses and IPv6 addresses always are accompanied with a subnet mask. The subnet mask itself defines how these hosts can communicate. Remember what I talked about when I said, okay, the PC wants to talk to a destination. Let's say that this, that's not a PC, that's a switch. Let's try that again. PC wants to talk to somebody else, another destination. Okay? Now think about this for a second. This guy has an address of 192.168.10.62. All right? 192.168.10.62. And he wants to talk to a PC with an address of 192.168.10.66. Okay? Question. Is this PC on the top going to have to go to a gateway? How do you know? Maybe. You can make that assumption. You could say they're both under the same network if you say, well, the mask is this or the mask is that, but I didn't give you the mask. If the mask was 255, 255, 255, let's do 224. Are they in the same subnet? No. They're actually not. If I change that from a 224 to a 128, I change what bit? 224 to 128. Are they in the same subnet now? Yeah. Now they're in the same subnet. That's what I'm talking about. When you change the subnet mask, it changes how the host communicates. Now, I don't expect you guys to know by changing the mask from 224 to 128, how does that affect the communication? Because we haven't done that yet. That's part of our discussion in subnetting. But what I'm trying to hammer home is that it's extremely important to understand the effect that a subnet mask has on network communication. Okay? We're going to learn about that effect as we go through this chapter and the next chapter and so on. The other thing that I want to point out is there are multiple ways of writing a subnet mask. In fact, you guys have seen it. You saw it on the topology diagram for the lab in the last chapter. You have the dotted decimal way of writing a subnet mask, and then you have something called prefix notation. Prefix notation. Basically, it's just a shorthand way of writing a subnet mask. Prefix notation. All right? Does anybody have any idea how I got 24 from that mask? What does the prefix represent?
But there's the one part of the number. They add up to 24 because there's 24 network bits.
Right. Now, let's just state that simply. It's the number of ones in the mask. Right? You're correct. It represents the network portion. We'll get into that in a second. But basically, the slash notation, the prefix notation, simply represents the number of ones in the mask. That is it. If I say /12, there are 12 ones in the mask. If I say /16, there are 16 ones in the mask. Now, what do I mean by 16 ones in the mask? I'm talking about from the left to the right, how many consecutive ones exist. That's another thing that you'll discover about a subnet mask. Subnet masks define the network that you belong to, and then they define the available hosts within that network. The ones portion of the subnet mask always represents the network you belong to. The zeros portion of the subnet mask represents the hosts within that network.
So that means in this network, I have 24 IP addresses?
No. It means that there are 24 ones in the subnet mask.
Yeah,
That's it.
I understand it.
It doesn't mean there are 24 addresses. It means that there are literally 24 ones in the mask, period. Okay? So if I give you /16, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. And the rest is 0. So that's a 255, 255, 0, 0. All right? If I give you a /22, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, that's 16, 17, 18, 19, 20, 21, 22.
0, 0, dot zeros.
0, and then the rest zeros, right? And one more 0. So this mask is 255, 255, what? 252, dot 0. 128 plus 64 plus 32 plus 16 plus 8 plus 4. That equals 252. All right? One of the things that you guys will have to be able to do on the exam, you'll have to be very good at it actually, is converting prefix notation to dotted decimal notation. When we do our subnetting discussion, you'll know exactly what I mean by that. Very, very important. Okay? The subnet mask can only be written, and this applies to IPv6 as well. The subnet mask can only be written as consecutive ones followed by consecutive zeros. You will never see a subnet mask that has ones and zeros mixed together, because the ones represent the network portion of the address, the zeros represent the host portion. What about IPv6? IPv6 uses a 128-bit address. So I can have a /40. I can have a /90. I can have a /124. Well, guess what that means? What does /40 mean? Not what it converts to. What does /40 mean? Period. 41's in the mask. That's it. What does /90 mean? 91's in the mask. What does /124 mean? 124 ones in the mask. See what I'm saying? All right? Just the number of ones in the mask. By the way, everything that we're learning about IPv4, it carries over to IPv6. You guys are going to be as proficient with IPv6 when we're done with our discussion as you are with IPv4, because it's all the same math. It's binary, period. It's binary. All right? All right. Absolutely. It's what I'm here for. Okay? All right. We still got a lot to go. I mean, there's some good stuff in this chapter. Trust me, it's good stuff. What I did is I went ahead and I created a couple of tables here. And I think these tables will help you out significantly, particularly the one that you see on the bottom right corner. If you can somehow, before you go take your exam, put this table to memory, and you can recreate that table when you sit down, because you're allowed to write stuff down before you start your test, as long as you're doing it while you're sitting there. If you can somehow duplicate that table, that will save you a significant amount of time on the test. And here's why. If I said, what is the mask, or what is the dotted decimal mask for /14? Very simple. Here's /14. It's a 252 in the second octet. What is /20? It is a 240 in the third octet. Okay, so what does that mean? /14, if it's 252 in the second octet, what is it in the first octet? 255. And what is it in the last two octets? 0, 0. That's right. /27, 224 in the fourth octet. /22, 252 in the third octet. Okay? It's just a quick way of converting from prefix notation to dotted decimal notation. All right? You may want to earmark this page because when we're doing our calculations later, this is going to help you when you're doing your calculations. What does this table up here represent? This represents all of the possible values that you can see in an octet. You will never see a 125. You'll never see a 133 because that wouldn't follow the rules. Consecutive ones followed by consecutive zeros. All right? 0 means no bits. 128, 1 bit. 192, 2 bits, and so on. So how did I get 248 from this number? The 128 plus the 64 plus the 32 plus the 16 plus the 8 equals 248. Joseph asked the question, why is /16 listed twice? Because it's a major network boundary. There are essentially three major network boundaries. /8, /16, and /24. All right? /16 is a 255 in the second octet, but it's a 0 in the third octet. /24 is a 255 in the third octet, right? But it's a 0 in the fourth octet. So it's kind of just a placeholder. That way all the columns lined up nicely. All right? By the way, you could take this table all the way down to /0. In the first octet, you could have /0, /1, /2, /3, but we don't really get into supernetting in this class. Well, we do a little bit in the form of route summarization, but these are the octets that you have to deal with. All right? The second, the third, and the fourth octet. Any questions so far? How much time do you get on the exam to write down information before it starts? Well, there's a little trick I'm going to tell you about because it depends on the testing center, but there's a tutorial that starts at the beginning of the test to tell you how to navigate the test and all that. You get 14 minutes for that tutorial. But when the timer for the tutorial stops, it doesn't automatically start the test. It just sits there on the screen. So you could stay at that screen for 20 minutes or 30 minutes or an hour or 2 hours if you wanted to. The test only starts when you literally hit start, in other words. So there is no limit. You get 90 minutes for the exam. That means when you hit question number 1, you get 90 minutes. If you want to sit there for a half an hour writing things down, you can do that because they're not allowed to skip you past the tutorial. They can't just put you on question 1 and say go. So they're going to put you at the tutorial and you can sit there as long as you want. Okay? All right. So this table, I kind of don't like this table that much, but it is where we come from, and it's always good to know where we come from, to know where we are today. In IPv4, this doesn't exist in IPv6, but in IPv4, the folks that came up with IPv4 back in the day, they said, you know what, we're probably not going to have that many people using the internet. We're not going to have that many computers. So let's go ahead and define boundaries for the classes. And let's say, okay, if your address falls in this range, then you're always going to use this mask. And in fact, they even designed that concept into the routing protocols. They basically wrote the routing protocols to say, you just assume what the mask is. You don't get to change the mask. You don't get to configure the mask. You don't even send the mask with your routing updates because all you do is you look at the first address block or the first octet of the address and you assume that the mask is that, or that based on those address blocks. This is what we call classful addressing. Classful addressing means that based on the address, the octet of the first, the address of the first octet, the number of the first octet, we would always assume that that address has that mask. It was fixed, but think about that concept for a second. Because this is the way it would work. You have a router with an interface, and you put 123.12.12.12 on that interface. On that interface, you didn't assign the mask because the mask was assumed. It was in the class A range, so it's a /8. But what did that mean for that interface? That was a network that supported 16 million hosts. Who's going to put 16 million hosts on a single network interface? Nobody. But that's the way it was defined. All right? That's the way it was defined. It's very difficult to kind of understand that concept today, because you think about it today and you think there's really, I mean, the most number of hosts we'll put on a subnet, maybe 5,000. Anything above 5,000, we start to really see communication issues. But before subnetting, we could not adjust the mask. And that's essentially what subnetting is. Subnetting is taking the mask and making it classless, meaning not using the mask that was predefined for the subnet. So you had 128 networks here and 16 million hosts per network. So behind one router interface, you could have 16 million hosts, and that was it. So you can imagine when these Class A addresses were being assigned, there was so much wasted address space. Who is getting these Class A addresses? Well, yeah, you might have had some big service providers. And what were these big service providers doing with these addresses? They were doing layer 2. It was just a big switch network. So they might have 10,000, 20,000, 50,000 hosts on some sort of layer 2 network. So the concept of classful addressing hasn't existed for a very, very long time. Classful addressing has not existed for a very, very long time. We still kind of define addresses into classes, but the concept of classful addressing has been, well, it went away in the 80s, all right, when networking was first being developed. But you do need to know the classes. Class A was 0 to 127, mathematically 0 to 127. But of course they said, well, let's not use the 0 subnet. That's going to be our undefined network, which means there goes 16 million addresses. And by the way, the 127 subnet, we're going to reserve that for something called loopback testing, meaning allowing a host to test its protocol stack. They didn't just assign one loopback address for that purpose. They assigned an entire Class C or Class A block for that purpose. Most people, when they ping their loopback, I mean, I'm sure many of you have seen this concept before. If I ping my loopback address, ping 127.0.0.1, if I get a reply, what am I testing here? What's actually being tested in this scenario? Am I testing my network adapter? Am I testing the network? The answer is no to both of those. I'm testing the protocol stack. I can disable all my network adapters and this ping will still work as long as the protocol stack is working. See, you guys are way too young to remember this, but back in the day, you used to have to actually install the protocol stack. It wasn't built into the operating system. You would actually have a set of diskettes. Google that if you don't know what that is. A set of diskettes that you would have to load your network drivers from. And the network drivers would determine,
That's in Windows 95 and 98, right?
way before that. Windows for Workgroups, Novell, right? DOS. So in this particular case, when you ping a loopback address, you're testing the protocol stack. You're testing the software. But guess what? You can ping any address in the 127 range, and it does exactly the same thing. The entire 127 block was reserved for testing the loopback. 16 million addresses to do the exact same thing. Obviously, when they were doing this, they didn't really think too far ahead. They didn't think about, we might need a few of those addresses. In IPv6, they were smarter. There's only one address in IPv6 for testing the loopback, and that is :1. All right? So I'm not connected to any IPv6 networks on this host, but if I ping :1, it responds. That means IPv6 is running on my machine. I've got an IPv6 protocol stack installed. Okay? Obviously not the point of this particular slide here, but that's why they have the double asterisk there, because the 127 was kind of reserved. So even in the Class A space, 0 went away because it was reserved. 127 went away. In the Class B range, it was 128 to 191. Class C, 192 to 223. The predefined masks /8, 16, and 24. Remember on the last slide, I talked about major network boundaries? This is what they mean when they say a major network boundary. They're talking about Class A, Class B, and Class C. All right? Class D is used for multicast, 224 to 239. Class E still isn't used today, experimental. Experimental for what? I don't know, but not used today. What changed to get rid of this whole concept? What changed to allow us to get away from this classful concept? You'd be surprised. Routing protocols. Original routing protocols didn't send subnet mask information with routing updates. So they started to write the routing protocols to actually send the subnet mask information with the routing updates so that we didn't have to assume what the mask was. Additionally, the protocol stacks on the computers were redesigned so that you could set the mask instead of assuming the mask, and so on. All right? Now, as far as what you need to know on this slide, you're going to need to know the ranges, 0 to 127, 128 to 191, and 192 to 223. But that's something you just kind of have to memorize. All right? We don't worry about classes anymore too much, though. Everything is, what's the mask, what's the IP address? If I know the mask and I know the IP address, then I know everything else. Wait till you see how I teach you guys subnetting. That will blow your mind. All right? All right. By the way, in IPv6, we don't have classes. We never did. IPv6 never had predefined subnet masks. Another thing that got introduced in IPv4 is this concept of private addressing, what we call RFC 1918 addresses. RFC stands for Request for Comment. It's just a document that's written to define a standard. And in the case of private and public addressing, it was RFC 1918. You'll see actually a reference on the exam to RFC 1918, so you need to know that. What was happening in the world of networking that caused us to even define these ranges? We were running out of address space. So what the IANA did, and the other folks that were defining addressing, is they said, you know what? Instead of giving everybody public address space, for their internal hosts, let's go ahead and set aside some networks that can be used by anybody, but not route them on the internet. That's what we call the private address ranges. The entire 10 network is private. The entire 172.16 to 172.31 network is private, and 192.168 is private in each of the classes. What does it mean for an address to be private? It means that it's routable, but it's not routable on the internet. So in order for you to go to the internet, what do you have to do with that address? You have to translate it to a public IP, right? If I look at my computer here, and I do an IP config, my address for my wired interface here, I've got a bunch of them on my computer, hold on. My address on my interface is 10.10.10.5. That's in a class A space. Is this a classful address or is it classless?
This is a class?
It's classless. How do I know it's classless? Because the address and the mask don't match. 10 should be a /8, but it's not. It's a /24. It's just a subnet. But that's not the address that I'm using to get to the internet. If I open up a browser here, all right, and I go to ipchicken.com, this is the address that I'm being represented as on the internet. 12.23.158.146. So my 10.10.10.5 address is being translated to 12.23.158.146. Okay? All right? Why did they have this definition of private addresses? They had this definition of private addresses because they wanted to preserve those public addresses for routing on the internet. So they started telling people, go ahead and convert to private addressing and just set up a NAT boundary at the edge of your network and do your translations on your edge device.
How do I reserve an IP address? Let's say I'm creating a network, and I want to have my network to have all IP addresses. How do I reserve those?
Well, it's practically impossible to do today in IPv4. The question was, how do I reserve? What if I wanted to use public addresses for my network? Most ISPs, first of all, the regional internet registries, we'll talk about those later on, they don't have any more addresses. IPv4 has been completely exhausted. Service providers still have address blocks that they can assign, but very, very rarely, in fact, almost impossible for you to convince a service provider to give you a block of 100 addresses or 1,000 addresses or whatever. What the service provider typically is going to do is they're just going to assign you a block of 8 addresses or a block of 16 addresses. And you can use those addresses to do your translations. See what I'm saying? So you do private addressing inside your network, and you do translation of those private addresses when you leave your network. When you open up a business or whatever, you go to a service provider, you say, I want internet access. They're going to drop a circuit at your location. That circuit is going to be public domain. It's going to have public addressing. And they're going to give you a block of addresses on that circuit. But they're not going to give you a block of addresses for every host inside your network. They're going to give you a block of addresses that you can translate to. So inside your network, you're running private addressing. Outside, you're running public.
What do you mean by outside?
When you go to the internet.
Oh, okay. Okay.
Addresses get translated.
So the private, I can assign it, for example, for domain controller.
Anything.
The DNS server.
Let me simplify this as best as possible. You have a router at home for your internet. That router has a connection, usually DSL or a cable modem, to a service provider, and it has a LAN. This is 1918 addresses. This is public. And usually it's only one public address on that interface. So if you're using RFC 1918 addresses internally, you can do whatever you want. It doesn't matter. You can make a Class A network with 16 million hosts, or you can make a Class C network with 254 hosts. It doesn't matter what you do. But these RFC 1918 addresses are not routable on the internet. So you do something on this router called network address translation. When you want to go out to the internet, you translate your host internally to this address, and then you go out to the internet.
Okay, I kind of understand it now. Let me just say this, and you confirm if I understand it correctly or not.
Okay.
Let's say I got a private IP address of 192.168.2.2.
Right.
Okay, and inside my network, I assign this to my domain controller.
Right.
That means anyone outside the world, if they try to reach to 192.168.2.2, he'll get something else. He's not going to get my domain controller.
Yeah, nobody can get to 192.168.2.2 because it's not routable on the internet. Now, the way that works in a business is you have probably a firewall at the edge of your network. That firewall has an outside interface, an inside interface, maybe a DMZ, okay, where you have your public servers. Maybe you have an HTTP server here, FTP server, or whatever. What happens is the service provider, it's the same concept. It's just a bigger scale. This is private. This is public, right? And the service provider has a public address on your firewall, but they're also sending you a block of public addresses that you can assign to your devices. Now, this HTTP server has a private address, but you have rules in this firewall to say public address 1 translates to this private address. So if somebody wants to talk to that web server, they're going to go to that public address, and that's going to get converted to that private address of that web server. Now, of course, we're getting off track here, but we do have an entire chapter on network address translation. So we're going to see all these concepts about translations a little bit later on. Yes, sir?
Just a quick question. I don't know. I know it's not like practical, but like let's say inside the private IP or like the private network, can you use other values for the IP? Like let's say Class A starting with 11. Yes,
you can.
Okay. But it won't affect anything.
See, that's the thing. There is no law that says you can use any address, right? The question was, could I use 11? Could I use 12 inside my network? Actually, you can. You're running the risk of having a problem because somebody owns 11 or 12 in the real world. But as long as you're translating 11 or 12 to a real address before you leave, there's nothing that says you can't use 11 or 12. See what I'm saying?
Yeah.
Now, it's probably frowned upon if AT&T owns 11 and they're assigning 11 addresses to their customers and somehow you're using 11 inside your network. It's hidden because you're translating it, but if somehow that gets published or the host doesn't get translated, then you're trying to spoof somebody else's address.
Yeah.
But what you do inside your network is completely up to you. You could set up your home router at home to use 209. There's nothing wrong with that. As long as when you do your translations, you're translating to a real IP that is routable.
Okay. What about like just for multicast address? Like does the router know that those specific values are reserved specifically for multicast?
Yes, you can't assign multicast addresses to hosts. You can't assign 127 addresses to hosts. The software, the protocol stack is written in a way so it won't let you do that. The experimental range you can't assign to hosts. Okay, so it's not going to let you do that. You would need to either have your own DNS or do host records to prevent going out that way. Yes and no, right? As long as you're doing translations, nobody knows what your inside addresses look like anyway, right? Even if you have a publicly facing server and you gave it a public address that belonged to somebody else, as long as that publicly facing server was being translated to an address that was assigned to you, nobody's going to know the difference. But the translation has to be the address that's advertised, not the one that's physically assigned to the device. All right? Again, we'll get into the whole concept of NAT, and we'll talk about NAT in a lot of detail in a future chapter. All right? Now, with regard to special addresses, this is where this is going to answer a lot of the questions you guys have when you were doing your lab exercise. In IPv4, there are reserved addresses in every single subnet. The most common are the very first address and the very last address. The very first address is what we call the network ID. If you recall, the network IDs in our topology were 10.0, 11.0, 224, right? The network ID is not assignable to anything. The network IDs are used to define the network in things like routing tables. It is literally the name of the network. What network do you belong to? I belong to the 10.0 network. Okay? This seat that you're sitting in is your address. The name on the room is the network that you're in. You can't give somebody that name because everybody belongs to that network. So the very first address, and this applies to both IPv4 and IPv6, the very first address is always reserved for the network. Is it always 0? No. Network IDs are always even numbers. You'll never see a network ID like 11.11 or 11.17. But you will see network IDs like 11.192 or 11.64. Network IDs are always even, meaning the last address, right? It's always the very first address in the network itself. The last address, and this only applies to IPv4, but the last address is what we call the broadcast address. If I want to send a packet that goes to everybody in that network, I send my packet to that address. And that's always an odd number. A lot of people think 255. Well, 255 may be a broadcast. It may not be. It depends on how the network is constructed. We already talked about the concept of loopback. The entire 127 block is reserved for loopback. We didn't talk about link local. Link local also stands for, is referenced as a PIPA. Microsoft calls it a PIPA address. Basically, when you get a 169.254 address, that means that the client was not able to obtain an address through DHCP, and they don't have an address statically assigned. Most of the time, a 169.254 address means that you can't communicate. But actually, it is a usable address. You can use 169.254 to communicate, as long as you have other hosts on that network that are programmed to respond. Okay? A lot of times you'll see this type of addressing used for workstations that are called diskless workstations. They don't have any hard drives. They boot up into memory from another device on the network. The experimental class, we already know what that is. And then we have the all hosts broadcast address. 255, 255, 255. Just another specially reserved address that's actually used quite often. It's used in DHCP, for example. Right? Think about it for a second. I'm a DHCP host, and I'm trying to get an address. I don't know what network I belong to. I don't have an address to communicate, but I have to send my packet somewhere. Well, guess where I send it? I send it to 255, 255, 255, 255. Now, that does not go past the router, but it will go to every host in the subnet. All right. So we already kind of talked about this concept as well, classful addressing. Classful means we're following the rules of the major class boundaries. Classful is bad, but what is classless? Classless means we're not following the rules of the major network boundaries. Classless addressing is essentially subnetting. It can also be supernetting, by the way. Supernetting is the opposite of subnetting, where you make the network smaller, but you make the host range larger. Subnetting is where you make the host range smaller, but the network range larger. Classless routing, classless addressing, basically means you're just not following the classful boundaries. We have a question from Brad. Why don't APIPA addresses get included in ARP tables? APIPA addresses are locally dynamically assigned, so I'm not sure. I've never used an APIPA address technically to build a network. I've always just worked with DHCP or static addressing. I would imagine in a network that uses APIPA addressing, the ARP process would still be the same, as long as you have other hosts that you're communicating to in that same range. I don't know, I've never looked at that. But, you know, rules are rules, right? Think about the concept here. If I open up a browser and I happen to know that my network is using APIPA addresses for assignment, and I type in a 169.254 address in my browser, my machine is still going to try to resolve the MAC address for that destination. I would think so. Have you had experience where you don't see MAC address entries for APIPA addresses? Remember, those ARP cache entries are only going to go into the table if there's actual communication taking place. So maybe you won't see it initially because the APIPA address becomes essentially an unusable address in a normal network. It says here, I occasionally have machines that come from one network to another and they fail initially to get DHCP. Yes, well that's true, yes. And that's when they will assign themselves an APIPA address. By the way, I'm going to tell you why they're failing to get another address. All right, I picked them up from Nmap scan and use, for rogue detection, yeah. Oftentimes the DHCP process fails when you're moving hosts from network to network, and it doesn't really have a whole lot to do with the fact you move the host. It has to do with the fact that spanning tree is delaying the DHCP process, the ports are not being activated in a quick enough time, and so on. There may be some other stuff related to DHCP directly with hosts moving, but that's generally what I've seen. All right. Let's see. It's usually when they come off of wireless and then go on to wired. Okay. So who is responsible for assigning address blocks around the globe? We know who the chief is, right? The chief is the IANA, the Internet Assigned Numbers Authority. All right? Those are the guys that handle the allocation of address space. But we have these things called regional Internet registries. There are 5 different regional Internet registries that exist today. In North America, ARIN, in Latin America, LACNIC, in Europe, right? In Asia, APNIC, or Asia Pacific, and Africa, AFRINIC. So here's how it works. These regional Internet registries get allocated blocks of addresses from the IANA. The regional Internet registries then allocate addresses to customers, service providers typically. Then the service providers allocate addresses from their blocks to their customers. It's a hierarchy. It's a hierarchy. All right? Unfortunately, with regard to IPv4, there are no more IPv4 addresses that are available from the regional Internet registries. No more blocks. The only blocks available are from our service providers. But this is the same architecture that we use for IPv6, and these regional Internet registries are still assigning address blocks in IPv6. Speaking of IPv6, why do we need it? This is an extremely interesting discussion. I think you guys will enjoy this. All right, we already talked about kind of the benefits of IPv6, more address space, less complex header, a lot of enhancements to security, customizability and functions, you know, but there's a lot more to IPv6 than even we talked about originally. We already know that IPv4 is pretty much used up. Now, does that mean IPv4 is going away anytime soon? Nah, it probably will never go away. All right, there's always, dual stack is probably where we're going to end up, where we're running both stacks. But IPv4 will never go away.
So what was the reason for inventing IPv6?
Well, the reason for drafting IPv6 and IPv6 standard was because they knew they were running out of address space. And you have to understand, the methods that we use to protect IPv4 were not designed originally into the protocol. NAT, private addressing, and this concept of routable, non-routable addresses just didn't exist originally. All right, we have a question here. Who are our main ISPs? Well, we're going to talk about that architecture here in a second, but you can kind of envision the architecture as a tree structure or a tiered structure of service providers. We have what we call tier 1 providers, then we have tier 2 providers, tier 3 providers, and so on. There are about, and don't quote me on this number, but it's pretty close, there are about 17 different tier 1 providers around the world. AT&T, Verizon, Sprint, Deutsche Telekom, L3, and some others, right? These tier 1 service providers are designed, well, they have relationships with each other to route traffic across the internet. They have really, really expensive routers that have millions of routes in them, and they make up the internet. I don't know if Liberty Global is one of them. You'd have to Google tier 1 service providers and you'll get a list of them, but I'm not sure if Liberty Global is one of them. Comcast, Time Warner, those guys are not tier 1 providers. They're very, very companies, but they're not tier 1 providers. They're actually tier 2 providers, or maybe tier 3 or whatever. Okay? But here's how it kind of works. you've got, if you look at the overall structure, let's just take Aaron, for example. So Aaron is going to assign blocks of addresses to your Tier 1 ISPs. Now, those Tier 1 ISPs can work directly with customers. Companies like Cisco and Bank of America, they like to deal with those Tier 1 ISPs because they're at the core of the internet, and it gives them the most redundancy, the most resiliency, the fastest routing, etc. But these Tier 1 ISPs can also have relationships with Tier 2 ISPs, and those Tier 2 ISPs and so on. Now, you as a customer might be attached there. I'm attached there because I'm an AT&T customer. AT&T is a Tier 1 provider. Okay, but if you have HughesNet, for example, they might be Tier 3. But it's all routing. The Tier 1 providers route to the Tier 2 providers. They route to the Tier 3 providers. But the backbone of the internet is this Tier 1 level. Okay, let's just do a quick Google search. And see what comes up here. The Tier 1 Club. Who are the Tier 1 ISPs? In the U.S., AT&T, Verizon, Sprint, CenturyLink, L3, NTT, and Cognet. And let's do Europe here. In Holland, KPN. The UK, British Telecom. That makes sense. In Sweden, TeliaSonera. India, Germany, Deutsche Telekom. In Spain, Telefonica. In France, France Telecom, and so on. Right? There aren't a whole lot, though, if you look at this list. So I think my number is pretty close. All right? I mean, in the U.S., we only have, what, 7? They said maybe. Maybe Cogent is Tier 1. I'm not saying that that list is accurate either. We know that everything on the internet is true, right? Okay? But that's essentially how it works. You've got your regional carriers, you've got your Tier 1 carriers, and so on. You can see things like how much 410,000 miles of fiber, CenturyLink, Cogent Communications, Deutsche Telekom, Global Telecom, KPN, L3, Liberty Global. Okay, they are a Tier 1 provider, Liberty Global. NTT and so on. These guys make up the internet. And let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I was very close, right? 18 Tier 1 providers. All right? So that's how the structure of the internet works. Not all traffic on the internet flows through Tier 1 providers. If you're connected to a Tier 2 provider and another customer is connected to the same Tier 2 provider, there's no need for you to travel through the Tier 1 provider to communicate to them. But I guarantee you most of the major world's internet traffic goes through those Tier 1 providers at some point.
So traveling from Tier 1 to Tier 2 to Tier 3, does that make the signal weak?
No, it's just routing.
Routing.
It's just routing. It's like saying going from building 1 to building 2. Does that going to make the signal weak? No, it's just routing, right? It might increase the amount of delay. That's how we really measure communication in the network. We measure it in delay. But again, remember we're talking about milliseconds of time. You see what I'm saying? And these routers have really, I mean, they're huge routers. You know, they're the size of a refrigerator, and they have massive processors and massive amounts of memory, and really expensive cards in them to provide this backbone. Okay? So IPv6, as I mentioned before, IPv6 provides us with really limitless number of IP addresses. Wait till you see how IPv6 works in the real world. It's amazing, okay? Which we'll get to in this chapter. IPv6 has IPv4 theoretically has a maximum of 4.3 billion addresses. Sounds like a lot, but it's not. If you think about just having one address per person on the planet, it's not enough. But you think about all of the devices that you have attached to the network, one person can't just use one address. You're going to need lots and lots of addresses. So IPv6, because the address space is 4 times larger, exponentially has many more addresses, 340 undecillion addresses. 340 times, or 3.4 times 10 to the power of 38. Now, the challenge that people have with IPv6, and I'm going to hopefully convince you that it's no longer a challenge, is the way that an IPv6 address is written. IPv4 is simple enough, 192.168.201.113. Look at the IPv6 address, A524:72D3:T2C, etc., etc., etc. That is literally an IPv6 address. Now, can you imagine being on a support call and trying to help somebody out and saying, I need your address, and they're having to read this whole address off? Well, guess what? That's not quite the way it works. So I'm going to explain why that is in a little bit. In fact, with IPv6, addressing is simpler than IPv4.
Yeah.
I'll show you in a little bit. Okay? Not very long from now, I'll show you. Can IPv4 and IPv6 coexist? Absolutely. There are completely separate protocol stacks. IPv4 and IPv6 are unique protocol stacks. They're not compatible with each other, first of all, because they use completely different addressing formats. The headers are different, so you can't just have an IPv4 host talk directly to an IPv6 host because of the formatting, all right? But the concepts are still the same because ultimately it's binary communication. When you deploy IPv6 and IPv4 at the same time, this is called dual stack, and this is probably one of the most common migration methods that you'll see, where you run both stacks at the same time. We're actually going to do this. We're going to set up a network in OSPF, and we're going to dual stack that network. Okay? Not today, though. The other option you have is you can do tunneling, where you could say, okay, I want to run IPv6 in my offices, but my service provider doesn't support IPv6, which doesn't happen today. But so what do? You create a tunnel. It's called the 6-to-4 tunnel, and you encapsulate your v6 datagrams inside of an IPv4 datagram. You basically make your IPv6 packets payload, and you transfer them over the service provider's network using IPv4. You can also do translation, a NAT 6-to-4 router where you can do network address translation, translating v6 addresses into v4 addresses.
Is that something would be on the router? It's called the translator?
Yep, the router would be the translator. The router would be dual stacked. It would have an interface in v6, and it would have an interface in v4, and it would have logic built into it or programmed into it to do the translations. Not as common. We typically will see this in service provider networks. What are the security concerns with NAT? Well, there really aren't a lot. Translating addresses is not a bad thing. I suppose from a security engineer standpoint, translations could be considered a risk because you're hiding the identity of the real individual, the real host. So from that perspective, it might be considered a concern. The translation device, the translation router or firewall or whatever it is doing the translations can be compromised. So you can compromise those translation rules or translation profiles. But as far as the actual translation, outside of those, I wouldn't really say that there are a lot of security risks in that regard. All right. So IPv6 addresses are written as 128-bit addresses, but they're written in hexadecimal format. They're written in hexadecimal format. Why? We could have written IPv6 addresses in decimal format. Take a look at how an IPv6 address is structured. It is 128 bits in length, and it's broken up into blocks of 16 bits. 16 bits, 16 bits, 16 bits, 16 bits, 16 bits, etc., etc. Those are called, well, there's 8 of those. Those are called hextets. All right? Hextet is a block of 16 bits. Now, if I was to write that in decimal, I could do that, right? Let me see here. My address is 12,384.192.16,000. No, I wouldn't be able to do that. 16,054. Yeah, you could do it that way. Because, by the way, 16 bits means 0 to 65,535. So any number in that range would fall within that 16-bit block. But it's actually easier to represent the address in hexadecimal format. Convert, here, let me show you. Convert 65,133 to binary right now. Do it. I'm being facetious. Don't do it. Well, you know how to do it. You have to write out your scale. You have to add up the ones. Convert 3C5D to binary. 0, 1, 0, 0, 1, 1. What is C? Let me write that again. 3C5D. 0, 0, 1, 1. What is C? 12, 1, 1, 0, 0. 5, 0, 0, 1, 0, 1. And D? 13, 1, 1, 0, 1. See how easy it is to convert hex?
Hold on. How did you figure out that the C is 12?
Because hexadecimal. 0 through 9, A through F. A is 10, B is 11, C is 12. Remember that? D is 13. Remember, hex is 0 through 9, A through F. So it's actually easier to convert hex to binary than it is decimal to binary, because you just look at each hex character individually. Does that make sense? So writing an address in hex, actually, it's not that bad. And the host. And what defines that boundary? What defines the boundary between the network and the host? The mask. Exactly. Sorry, I must have lost my audio there for a second. I apologize, guys. The mask. The longer the mask, the more networks, the less hosts. The shorter the mask, the less networks, the more hosts. It's exactly the same as IPv4. The only difference is the mask is 128 bits. All right? Now, there is a way to write out IPv6 addresses in a shorter format. There are 2 steps to doing this. The first step in shortening up an address is that leading zeros within a hextet don't have to be written down. The leading zeros within a hextet do not have to be written down. Why? Because I know how big a hextet is. It's 16 bits. So if I eliminate these zeros here and I eliminate these zeros here, it's not that they're actually gone. I'm just not writing them down. I can interpret what those values are, though. You cannot eliminate the trailing zeros. I mean, think about it. If I had 0, 1, 0, 0, and I eliminated that 0 and that 0 and that 0, how would I know if it's 0, 1, 0, 0 or 0, 0, 1, 0? I wouldn't know. Or any other combination. But by only eliminating the leading zeros, I can shorten my address. I'm not actually taking them out. When I write down the address, they just are written in a shorter format. Okay, so let's say I have 2001 colon DC3B colon 0001 colon 0030 colon 1000 colon 3CFE colon 00A0 colon 0001. That's my whole address. Well, I can write that out as 2001 colon DC3B colon 1 colon 30 colon 1000 colon 3CFE colon A0 colon 1. Right? All right, we didn't save a whole lot, but it's a little bit shorter. That's the first rule. The second rule is any consecutive range of zeros. Any consecutive range of zeros can be written as a double colon. So let's say I have 2001 colon 0000 colon 0000 colon 1000 colon 0000 1, 2, 3, 4, 1, 2, 3, 4, 5 colon 0000 colon 0000 6, 7 and 0001. Okay? 2001 quad 0 1000 quad 0 quad 0 quad 0 0001. I can replace either, I can only do this one time, I can replace either all of these zeros with a double colon, or I can replace all of these zeros with a double colon. So I would write this address as 2001 colon 0 colon 0 colon 1000 double colon 1. Make sense? You can only use the double colon one time because the double colon doesn't represent a specific number of zeros. It represents that whatever's left over is 0. Remember the loopback address? in IPv6? What is the loopback address in IPv6? :1. Remember I did a ping, :1? What am I actually pinging? Well, okay, 0000, colon 0000, colon 0000, colon 0000, 0000, 1, 2, 3, 4, 5, 6, 7, 8. That's what I'm pinging. You want to type that whole thing out? No. So just write :1. Okay? When you see a :: in an IPv6 address, it simply means that it references or it represents a string of zeros. All right? So here's some examples. In this particular case, we dropped this leading 0, we dropped these 3 leading zeros, we dropped those 3 leading zeros, those leading, and that leading, and that leading. And we have 8 consecutive zeros there, hexadecimal zeros. We have 8 consecutive zeros there. So in either case, I can choose to put the :: here, or I can put it there, but I can't do both. And either representation is valid. Either representation is valid. Now you're still looking at this, I know you are, and you're saying, well, that's fine, but it's still a long address. I still don't want to tell somebody my address is 2001 :db8 :abcd :0 0 100. Well, you're not going to have to. I'll explain why in a minute. Okay? So let's review before we move on to the next couple of slides. We have quite a bit left in this section here. We got about 35 minutes left. We should be able to finish this chapter. All right? Number 1, IPv6 addresses, 128 bits in length. Number two, they're written in hexadecimal format in blocks of 16 called hex text. Number 3, all IPv6 addresses are public. Number 4, there is no broadcasting in IPv6. I'm just doing a quick review. Number 5, IPv6 addresses can be written in shorthand notation by dropping leading zeros and by representing the largest block of consecutive zeros with a :: In addition, in IPv6, no more broadcasting. Now, somebody had asked previously, well, if there's no more broadcasting, then how do I send a packet to everybody? There is a special multicast address in IPv6 called an all hosts multicast address, FF02:1. This particular address, now you know what the :: means. This particular address, every IPv6 host is listening to that address. So if you really technically want to talk to everybody, that's the address you would send your traffic to. But there is a limitation to that.
FF0Z? No, 02.
It's hexadecimal. We don't have Z's in hexadecimal, right? That's fine. I want to point that out because I want you to think about that, right?
Yeah.
All right?
Only up to F.
Only up to F, right. FF means multicast. We'll talk about that in a little bit. But this is a scoped multicast, meaning it can only go a certain distance. So, but that's really the same concept we have in broadcasting in IPv4, right? In IPv4, broadcasts don't go past the router. It's still the same thing in IPv6. Multicasts have a scope limitation. They can only go a certain distance. Certain types of multicast. All right, but we still have unicast. Of course, we have multicast. It plays a very, very important role in communication in the IPv6 world. And anycast, we talked about those address types in a previous chapter. All right. What about the prefix length? IPv6 does not use a dotted decimal subnet mask. The only way that we represent an IPv6 address mask is in the slash notation format. But you will see some strange numbers. You'll see /80 or /70 or /64. You're not used to seeing those numbers because you're used to dealing with 32-bit addresses. But you now know what it represents. A /80 simply means that there are 80 ones in the mask. /64, there are 64 ones in the mask. Does that make sense?
So the address will go as the whole address and at the end slash.
That's right.
Number of the hosts.
The prefix notation for the mask. Yep. All right. We have a little bit left here. So just like we had in IPv4, we have specific ranges of addresses that are reserved in IPv6. And you need to know these for the exam. There's no doubt about it. They're going to ask you stuff like this on the test. We already talked about the loopback function. Whoops. Let me go back. We already talked about this loopback address. That is the address that we use to test our protocol stack. What about the unspecified address, :? That is actually a valid address. What is the equivalent of that address in IPv4? Anybody? What is the equivalent address in IPv4 for :? 0.0.0.0. Right? All zeros. Okay? Not all ones, all zeros. Isn't : just all zeros?
Yeah.
The whole address is zeros. Well, guess what we use that for? We use that for DHCP. When a client is trying to get an address, it doesn't have an address, but it has to build the PDU. So what does it put for the source address in its DHCP discover? 0.0.0.0 or :. We use default routes. Default routes, which we'll learn about tomorrow, use all zeros as the destination. Okay?
Or the HTTP link for as a destination that we use the FS02::1?
No, it does not. There is in IPv6, there's a very specific multicast address for DHCP servers.
Oh, okay.
I can't remember what it is off the top of my head, but there's a specific group multicast address for DHCP and IPv6. It doesn't use one. That's a good question, though, because in IPv4, we use 255, 255, 255, 255, right?
Yeah.
Okay. Okay. The other one I want to talk about here, dang it, is this global space. Presently, and this is something that they did very differently in IPv6 that we didn't see in IPv4. Presently, what they have done is they've said, you know what? The address, first of all, we know in IPv4, 0 to 255 is our range of addresses, isn't it? Based on the first octet, 0 to 255 is our range of addresses. You write that better, 0 to 255. And that is based on the value in the first octet, isn't it? What do you think the range for IPv6 is represented as? If you follow the analogy, it's 0, 0, 0, 0 through F, 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 wouldn't it be? That's the first hextet. You follow what I'm saying? All of our address blocks are assigned from that range. If you go back and look at the chart here, there's 2000, there's FC00, there's FEB0, FE80, there's, well, :1, that's a special type of address. But every single block of IPv6 addresses is assigned from 0000 to FFFF. You can't have anything larger than FFFF because you only have 16 bits. But what they said in this case is they said, you know what, let's not go ahead and allocate every single block for the internet. Let's take a small slice of that block, 2000 :/3, and we're going to use that for our public address space on the internet. Now you look at that and go, well, one small block out of all of those ranges, that's all you chose, but that is a lot of addresses. You still have, a little tired late in the day, can't do the math, you still have 7 times 16 bits for addressing because we're only using 1 hextet to define the range. So what does it mean to say that all IPv6 addresses come from this range? What does it mean? Here's what it means. 2000 :/3. Do we know what that is? That's the mask, isn't it? Is /3 the subnet mask? Shake your head, yes, it is. Now, how does that translate to the range of addresses available for IPv6 on the internet? What is 2000 in binary? That is hex, right? What is 2000 in binary? 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. The first 3 bits are fixed. That's what the /3 means. The first 3 bits are always 0, 0, 1. Isn't it the same thing in IPv4? If I say 10.0.0.0/8, doesn't that mean that the first 8 bits are always that? Because the mask is 255.0.0.0. That is the network. It means exactly the same thing in IPv6. Every single global IPv6 address starts with 001. Which means, what is the actual range? What is the actual range of addresses? I got a special prize for anybody that can actually tell me the actual range. He says 2000 to 3FFF. Congratulations. That's correct. I'll figure out what I'm going to give you tomorrow. How do we get that? Because if the first 3 bits are fixed, that means that the remaining bits can be anything. Well, if that's a 1, then that's a 3, right? If these are all 1s, then that's an F. If these are all 1s, then that's an F. If those are all 1s, that's an F. So every single public IPv6 address comes from that range, 2000 to 3FFF. Which, by the way, is a lot of networks. If you do the math, we'll learn this math tomorrow, but let me go ahead and do the math here. How many bits is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bits, right? Let's see. 2 to the power of 13. That's easy enough. 8,192 networks. Doesn't seem like a lot, does it? However, how many bits are left over? How many hextets? There's 7 hextets left over. 7 hextets. Whoops. Oh, I didn't mean to do that. 7 hextets left over, right? 7 times 16, 112. So it is 8,192, 2 to the power of 112, times 8,192. That's how many subnets we're talking about, how many addresses we're talking about. Yeah, I don't know what that number is. It's really big, okay? It's a little overwhelming, actually, when you think about how many addresses exist. And that's just one slice. We haven't even talked about the 0000 block, the 4000 block, the 6000 block, the 8000 block, the A000 block, right? You still have stop it. You still, try this again. You still have the 000:3/3. You still have, well, the 2 that we're using, :/3. But then after that, you've got 4,000, you've got 6,000, you've got 8,000, you've got A,000, right? Then you've got C,000. Then you got E,000. You get the idea. All right, we had a question here. Would you please explain why 3FF instead of FFFF? Because the first 3 bits are fixed. We can't have 3F or FFFF. Remember, it's 2,000 :/3. So there are some bits in this first hex or the first hexadecimal character that are fixed. I didn't want to do that. Unmute all. That would be really bad. Okay, so if I look at 2 in binary, 2 in binary, 0010, those first 3 bits are fixed, meaning that they can never change. So the only bit that I can change is that bit. So in that first hextet, in that first block, that first hexadecimal character, it can either be a 2 or a 3. That's it. However, the remaining 3 hexadecimal characters can be anything. So they can be a 0, a 1, a 2, a 3, a 4, a 5, all the way up to F. Joe, did that answer your question? Okay. Okay, I thought the next octet was locked at 3FFF. Well, we're talking about hextets, right? This is just the first hextet. The remaining hextets can be anything. Only the first 3 bits are fixed. Can you, if we move 20 years into the future, when the IoT has connected every household appliance, jewelry, automobile, etc., in every country, would you, will that be enough in your opinion? Absolutely. Absolutely. You know, I know the rule is don't ever say never, right? We'll never run out of addresses. Yeah, that's what they said about IPv4. But the reality is, yes. I mean, there are so many analogies on the internet that describe how many addresses are available in IPv4, IPv6, and it's amazing. I mean, it's really, you just can't really comprehend it. I'm going to go through one more exercise before we wrap up today that kind of talks about that concept and we'll give you an idea of that range. Can you upload this chapter first, please, so we can review it? Math is failing me at 2 a.m. Yeah, I understand completely. Understand. Which is why we're not doing subnetting today. Subnetting is something we do in the morning. You need to be fresh for that, all right? That's the next chapter, yeah. Let's go ahead, though, and wrap up this chapter. There are still a couple of important things that I want to mention, all right, about this chapter. The EUI-64 process. Now, this is an interesting concept. In IPv6 in the past, and this is another component of IPv6 that didn't exist in IPv4, was this concept of auto-configuration, where a host could just use its MAC address to join. Can you hear me? Hello? Okay, now they can hear me. All right. Oh, it looks like we're having some internet issues here. All right. Now, let me explain the process here in general. In fact, I'm going to come back to this slide because I want to talk to you about why this EUI-64 process is important. All right. And so I'm going to jump ahead to this slide here, which is how hosts can join networks without actually using DHCP or without using any kind of static address assignment. This is a function that's built into IPv6. This PC that you see here has an IP or a MAC address, right? It has a 48-bit MAC address, as a matter of fact. And let's say that that computer wants to join the network. Through this EUI-64 process, which I'll go back and describe in a little bit, it can derive its own host address. I'm just going to leave it at that for now. We'll go back and look at the EUI-64 process in a second. But it can derive its own host address. And then it sends out a message on the network. And it says, hey, I want to join the network. What network do I belong to? The router then sends a message back saying, you belong to this network. And the router and the host, or the host marries that information from the router to the address it derived from its MAC address, and it joins the network without even using DHCP. And it is a routable address. It is a routable address. Okay? So let's talk about that EUI-64 process and why that's important. First of all, a MAC address, as we already know, is only 48 bits. What else do we know about a MAC address? It's globally unique by the way it's defined. Of course, in order for the host to join the network, it wants to generate a 64-bit host address. Well, if the MAC address is only 48 bits, the first thing that has to happen is we have to expand that MAC address. We add 16 bits in the middle, and it's always the same 16 bits, FFFE. Now this address is 64 bits. This becomes the host portion of the address for the client. There is one more step. We invert this UL bit. The UL bit is that universal or local, what we would call the IG bit. No, not the IG bit, the LG bit, right? They call it the UL bit, same concept. The reason we invert that bit is because it is a universally unique address, because it was derived from a universally unique MAC address.
So let's say the value of the MAC address that mean that the EUI 64 address means 0?
So this first hextet here, actually this is an octet, right?
Oh yeah, yeah.
Because it's 8 bits, not 16. But yes, if that was a 0, well, we'll call it 03, right?
Okay.
It won't be, because if you remember how MAC addresses are defined, that bit is reserved for a specific purpose. That bit is always 0 in a globally unique MAC address, isn't it? If you remember the construction of a MAC address, the 7th and the 8th bit are always 0 in a unique address, aren't they? Remember the IG and the LG?
Yeah.
Now, let's just say, for example, it's not, though. Maybe it's a locally administered address, MAC address.
Okay.
It doesn't matter. That bit still gets inverted. So if it's a 1, it becomes a 0. If it's a 0, it becomes a 1. Does that make sense?
Okay. So that bit usually was a 1. That means that that first octave will be
Right.
when it gets converted.
Yes.
Okay.
Yeah. That's right. Okay? Now, you might look at this and go, well, why do I need this? What is this for? Well, it's actually used for a very specific purpose. Okay? It's called the link local address. And this is something that's unique to IPv6 that we did not see in IPv4. Link local addresses. Every single device that is configured for IPv6 has a link local address. Every single device. This link local address guarantees the ability for that client to communicate on the wire. Okay? And we're going to see later on in other chapters as we go through the lessons, we're going to see where that link local address is actually used. The link local address has starts with FE80::10. All right, let's talk about what that means. FE80::10. That is a predefined range. All right, what is F in binary? 1, 1, 1, 1. What is E in binary? 1, 1, 1, 0. What is 8 in binary? 1, 0, 0, 0. What is 0 in binary? 0, 0, 0, 0. Agreed? What does the /10 mean?
That's 10, 1.
The first 10 bits are fixed, 10 ones. 4, 8, 9, 10. So those bits are fixed, which means a link local address can be anywhere from FE80 to what? We know it's FE something, right? Because those are fixed.
0, 8.
What about this one here? That can be what? What's the maximum? 11, right? So what is 11? B.
Yeah, sorry. Missed the vote, right?
BF, right? Because that can be anything. All right? They said B0. It could be BF, I suppose. All right? So FE80 to FEB, that is link local. Okay? Now, this is a special purpose address. And actually, we're going to see it's used all the time. It's used for doing things like neighbor discovery. It's used to, we use link local addresses to identify neighbors in OSPF and EIGRP. We use link local addresses to find next hops for routing in IPv6. Link local addresses are used to do neighbor discovery. We don't have ARP in IPv6. We have ICMP neighbor discovery. So there's a lot of reasons why we see this link local address. And as we go through some lessons in the future, some chapters in the future, we'll talk more about what this link local address does. All right? But there's a very specific thing to understand. If you look at the way a link local address is divided up, the first 64 bits are fixed. All right, and actually, if I look at this, now I know why it's not FEBF, because 54 bits of that link local address are fixed at 0. Only the first 10 bits are modified, so that's where we get that FEB from. Okay? But look at the last half of that link local address. It's EUI64. Just remember that. It may not make a whole lot of sense right now, but when we start to do chapters down the line, it'll make more sense why we have 64 bits identified. Which brings us to, well, actually, let's look at this as a demonstration, and then we have essentially one more thing to talk about. Here is the MAC address on my gigabit Ethernet interface. Just by turning IPv6 on this router, the interface generates its own link local addresses. How did we come up with those numbers? Well, it's simple. FC9947, split that in the middle, the FFFE goes in the middle. That's the first step, right? FC, if I convert F to binary, it's 1111. C in binary is what? $12, which is 1100. Right? So what do? We invert which bit? We invert this bit here, so this becomes 1110 and 1111. Guess what? FE80, every link local address starts with that. FE 9947 FFFE 75 C3E0. That's how that link local address was derived. Now, I get it. You might think, well, I still have no idea what that does. That's true. We haven't talked about that yet. But I promise you, you're going to see what that link local address is used for later on. Okay? In fact, the topology that we put together, we're going to be configuring IPv6 on that topology tomorrow. All right? Multicast, as I mentioned, I'm not going to spend a whole lot of time on this slide, but multicast, all multicast addresses in IPv6 start with FF. Every single IPv6 multicast address starts with FF. Just like in IPv4, we have a range of addresses or range reserved for multicast, we do in IPv6 as well. But it's a little bit different because the next 4 bits and the 4 bits after that allow us to define the time to live for that multicast traffic, what we call scoping of multicast. And honestly, I don't want to really get into the details of that right now. If we have time in a future lesson, I'll talk more about multicasting in IPv6. But you will see me talking about various multicast or well-known multicast addresses. Remember that FF02:1? That's every IPv6 host. FF02:2 is every IPv6 router. You're also going to see FF02:A, that is EIGRP, FF02:9, RIP, FF02:6 and 5, or OSPF, and so on. All right. This will be the last thing that I talk about in this section, and then we'll wrap it up. But this is probably the most interesting thing about addressing for IPv6 that you'll see. Remember when I told you guys not too long ago, I said IPv6 addresses are actually easier than IPv4 addresses. Well, here's the reason why, okay? And this is also the reason why a lot of people say subnetting does not exist in IPv6, even though that's completely wrong. Subnetting does exist in IPv6. But the structure for IPv6 is completely different. The mindset that you use to deploy IPv6 is completely different. Okay? Think about this for a second. In IPv4, if you're designing your IP addressing plan, what do you think about? If I tell you there's 100 hosts on this subnet, there's 50 hosts on this subnet, there's 2 hosts on this subnet, what do you do with your subnet masks? You try to design your networks to match whatever size of a network you have, right? If it's a point-to-point serial link, you put in a /30. If it is a network with 100 hosts, you put in a /24 or something like that, right? We don't do that with IPv6. In fact, almost every single IPv6 network that exists is a /64. Now they picked 64 because of the EUI64 process. But let me break this down. The IANA, of course, is responsible for addressing. And they assign addresses to the regional internet registries. Now, what block are we assigning from? This block. Got it? So I am taking this block here. When I say I mean the IANA. And I am subnetting that block down to a /23. Which means how many subnets did I create? We haven't done the math portion of this yet. We'll do that in the morning. But let me just do the calculation. 2 to the power, well, let's do 23 minus 3. Where's my clear? There we go. 23 minus 3, yes, I did that. That's 2. That's 20, right? So if I take 2 to the power of 20, that's 1,048,576 subnets in this range that I created. Who's getting those networks? The regional internet registries. Does that make sense? Okay. Now, what are the regional internet registries doing with each one of those 1 million subnets? They're subnetting them down even further. Come on. They're subnetting them down even further to a /32. How many bits is that? That's 9 bits, isn't it? So for every single regional internet registry, actually for every single network, 2 to the power of 9, which is the 512 networks. Now, multiply that times 1 million, and that's how many networks the ISPs are getting. 512 million networks. You guys follow the math? Follow the logic? This is that hierarchy that we were talking about with IPv6. Well, guess what the ISPs are doing? You're a company, and you go to your service provider and you say, I want an IPv6 network. They're going to assign you a /48. That's 16 bits. 2 to the power of 16 is 65,536. So now we've got 512 million times 65,536 networks. That is whatever that is. Is that trillion? 33,554,432,000,000 networks. We haven't even gotten to the host level yet. It's very, very interesting. Yeah, that should cover your house. Wait till you see what you get at your house. You get the idea. And this is just the 2,000 block. We haven't even looked at the 4,000 block, the 6,000 block, 8,000 block. See what I'm saying? Now, all that being said, so you're Cisco or you're a company, you get a /48. And I actually had an engineer from Yellow Pages contact me, and he said, hey, we got some IPv6 blocks. Can you help me subnet them? I don't know what to assign to my serial links. I don't know what to assign to my network. I said, make everything a /64. That's it. That's what you do. Every network gets a /64. Because with one /48 prefix, how many networks can you create? If you go to a /64, 2 to the power of 16. So with one /48 prefix, you can create 65,536 subnets in your own organization. Now, I'm not going to multiply that times the trillion number that we saw before, but you get the idea now. Subnetting changes in IPv6 because you don't worry about, oh, I don't want to waste address space, so I want to put a /30 here, and I want to put a /28 here, and a /27 here. No, you put a /64 everywhere. They chose 64 for the reason of EUI 64 also. Like Windows Vista and other computers, they didn't know how to assign addresses without a /64 mask, so everybody kind of used a /64 mask. All right. Now the 56, that means that you can do some additional subnetting, but most of the subnetting in a company is from here to here. And guess what? If you go to Comcast or you go to Verizon, you have Verizon Fios at home and you ask them for an IPv6 address, guess what they're going to give you? They're going to give you a /64. That's as low as they go. They're going to give you a /64, which means that you have public addresses 2 to the power of 64 addresses in your subnet, in your network. That should be enough for your house, right? It seems like a huge waste, and it kind of is, really, but why not? There's so much address space, it doesn't matter. If we can make it simple by saying, hey, everybody gets a /64, it makes your job much easier. But what does that mean for you as a company? Well, let's take a look at this example here. And we're going to do this later on, tomorrow, when we start to add on to our network here. But think about this concept. I was given a /48 from my service provider. This is my ISP here, and behind that connection is my entire network, okay? They gave me a /48. That /48 was 2001 0db8 ACAD. Isn't that 48 bits? 16 plus 16 plus 16. What does that mean for the addressing in your network? Every single subnet that you have in your entire network starts with the same 48 bits, right? So you can pretty much write that off. When you ask somebody what network they're in, they don't even care about the first 48 bits because you know the first 48 bits are the same for every single network. Which means your subnets are from /48 to /64. Well, that's what they did here. This is the /48. This is the /48. This is the /48. What subnet is this interface in? Subnet 1. What subnet is that interface in? Subnet 2. What subnet is that interface in? Subnet 3. So when I say, what's the address of your router interface, all you have to tell me is, that's 1:1. Or it's 2:1. Or it's 3:1.
So the mask isn't necessary. Well, I mean, it's not.
If you assume that the mask is /64, which if you standardize on that, you don't even have to worry about the mask. All you say is, and if you're a host, it's the same thing. Oh, oh, you're in building X. That means you're in the 1 subnet. What's your host address? It's 355. Or it's, you know, ACAD. Or it's, you know, whatever. See what I'm saying? It's a little bit kind of a weird concept to grasp, but actually that's how you plan subnets in IPv6. So it gets a little bit simpler. I know it's a lot of information, guys. We're wrapped up with this chapter. I know it's a lot of information, and quite honestly, I would have even loved to go even slower and spend another couple hours on it, but I know you guys are worn out. I appreciate you guys sticking it out. Tomorrow we're going to do some math. We're going to get into some subnetting. All right. What do we got here? We got a comment. We will see IPv6 prefix delegation setup. Will we see IPv6 prefix delegation? No. In fact, we've pretty much covered what we're going to be doing in this class. I do teach IPv6 classes where we spend the entire week doing IPv6. You would see something like that then, but not here. Prefix delegation is where the service provider can actually assign prefixes to customers and customer destinations. All right. Subnet to make it easier to track the network rather than to fit the network into the address. Is that a question or a statement? I'm trying to figure that one out. I think I know what Derek is saying. He's saying in the past, we would subnet to make sure that we weren't wasting address space to make sure that the network fits the subnet. Now we subnet for designation. I mean, we still have to have separate subnets. Routing requires different subnets, period. But it's much easier in IPv6. And I think this really demonstrates that concept, right? The first 48 bits are the same for all 3 networks. This is the subnet. This is the host in the subnet. So you don't have to have these addresses like 2001 DB whatever, ACAD whatever, the 128-bit long address. And we're going to do that configuration a little bit later on. All right?
Using